So now we'll give my third lecture on the chapter 4, electromagnetic waves on course optics, and this lecture is about the energy of electromagnetic field. So essentially I will be showing you how we can calculate the energy densities associated with the EMP field components, and what is then also the total energy density associated with the EM field. I will speak a little bit about the intensity and irradiance of light and what is their difference. And I will introduce a field quantity known as a pointing vector that tells us into which direction the energy is flowing. So essentially it's very similar to the K vector, but not exactly so. But I will try my best to elucidate their similarities and differences. And I will be doing a little bit of calculations showing that how we can actually then calculate pointing vectors and optical energy densities for different kinds of fields. So this is what I will be speaking about in this lecture, and I will now get started. So we have now derived many of the most fundamental properties of light. So for example, of the fact that when we have a time harmonic plane wave, then it is really a transverse wave, and we have derived the notions of truth that the E and B and K fields are mutually perpendicular and so forth. And what we will do here in this lecture is that I will try my best to show you how we can calculate the amount of energy that is associated with propagating electromagnetic radiation. And as we know, electromagnetic radiation, it transfers energy from point A to point B. So I would say that this is the main difference between an electrostatic field or magnetostatic field, that in those cases, the field does not really transfer energy as such. It may give rise to forces, of course, that we move charges, but that's not the same thing. It doesn't transfer energy as such as a field quantity. And this is, of course, what we want to understand, and sometimes we also want to take use of, so that we, for example, might be interested in trying to understand how much of energy in forms of sunlight and electromagnetic radiation we are receiving on Earth due to the fact that we are orbiting a sun, a huge star that is producing a huge amount of energy, and how we could, for example, try to take use of that energy by using photovoltaics. And the treatment that we will do can be done quite nice using the energy densities that have been introduced already in the electrostatics and the magnetostatics. So I do not show how we can derive these equations, but they will just take use of what we already know, or we trust that we could easily derive if we would wish to do so. So the energy density associated with the electric field is mu naught vacuum permittivity divided by 2 times the field amplitude squared. And this is the energy density associated with the electric field. And this is, we already know this from the electrostatics. And for the same kind of formulation, we can write for the magnetic field, and this is known from the magnetostatics, so that then the energy density associated with the magnetic field, that's 1/2 times mu naught vacuum permeability times the amplitude of the B field, B squared. And utilizing what we have already discovered, so that we had the speed of light, and we realized that the speed of light can be used to connect the amplitudes of E and B together, so that the speed of light was the inverse of square root of mu naught times epsilon naught. And please remember that this relation, that when we take the unit wave vector and we take the cross product with the E, that equals to speed of light c times b. And in the scalar form, of course, this equation was exactly like I already said, that it's a way to connect the field amplitudes together, so that we know that the amplitude E must be equal to c times b. So that the energy density of the magnetic field component then can be nicely written, so that this energy density UB is 1/2 mu naught times b squared, and then we can write this using the E field amplitude. So this will be of form 1/2 times mu naught times E squared divided by speed of light squared. And this can be written to be similarly epsilon naught divided by 2 times E field amplitude squared. And this, of course, is equal to the energy density associated with the electric field. And using this, we now know that the energy is equally distributed between both of these field components. And if we would want to calculate the total energy density U of the electromagnetic field, of course, we can just simply sum the U's together. So the total energy density U is UE plus UB, and this is equal to just basically epsilon naught times the field amplitude of the electric field squared. Or if we would want to describe it using the B field, we would have this relation. And now what we want to do next in what follows is that we want to understand how this energy propagates. And I will warn you that even though we have the wave vector k showing us the direction into which a plane wave component propagates, this is not always the case that the energy propagates in the same direction. It may seem impossible to you, but when we would be looking into propagation of fields inside a medium, not inside a vacuum, there might be a difference. So that the energy actually goes in a slightly different direction than the wave vector k points into. This is mystical, but this can be the case for a case of specific materials, birefringent materials. So for conceptual clarity, we restrict to considering a small part of a plane wave that penetrates a surface A during a time interval of t, and this has been clarified in the figure. So this is the kind of situation we're interested in looking at. So instead of looking at the whole plane wave, which is a slightly problematic quantity in terms of how much of energy will be in a plane that is infinite in size, we just only restrict into a small portion, and now light propagates through, and then in time interval of t, the light has propagated a distance of L, which of course is c times t. And the volume now will be the A times L. So part of the wave filling a volume, the V, is, as I mentioned, A times L, and we can also simplify that to be A times C times T. And this gives us a means to calculate how much of energy we have inside this volume. So we are considering a portion of a plane wave component, and it propagates through this kind of volume in a given time, so that then we can definitely calculate also the total energy density. And the total energy density is the energy density times the volume, and this can be written to be it's the energy density times the A times L. So this total energy now, this might be very confusing. This is in fact a capital U, so this is total energy, and this is small u, energy density. And if we want to calculate the total energy, we calculate the energy density with the volume that we're dealing with, and that gives us the total energy. And this can be written to be that the total energy U, capital U, is energy density U times A times C times T. A more useful quantity to us in future is called irradiance, and we will try our best to use S to describe irradiance. Sometimes also I is used, but then there's always possibility that we confuse irradiance between the intensity. So I will try my best to use irradiance S during this course. And this tells us the amount of energy density that penetrates the surface A. And this is how we define irradiance. It's energy density that penetrates a given surface A during a time interval of t. So in another way of saying, in unit time. So the amplitude of this irradiance, it can be, of course, can be and will be generalized to be a vectorial quantity, a so-called Poynting vector. But just now we're looking into the amount of irradiance, so we don't yet generalize into vectors. So S equals the total energy divided by A times T. So that could be also written to be energy density U times speed of light. And then, of course, here we can place in the energy density, the total energy density, and then we will get C times epsilon naught times E squared. And if we want to write it using both E and B fields, we have C squared times epsilon naught times E times B. So this is a irradiance S in terms of scalar quantities. So these are the amplitudes of E fields and B fields, and this is the speed of light. And in the later parts, we will generalize this to be a vector quantity, because of course we could imagine that if here irradiance tells us of how much of energy is going through a given surface in a given unit time, that we might also want to be looking into different directions. And that's why we want to generalize our parameter here. In common language, like I already warned, irradiance is often called intensity, although intensity has a little bit different technical meaning. If you're interested in looking into that, I really recommend you to go into that link, clicking that out in your notes, and I think you will go into a Wikipedia article regarding these different units and different parameters that describe electromagnetic fields. And what I will do next is that I will generalize our treatment to vectorial quantities, and this gives us irradiance kind of propagation direction, where this energy density per unit time interval is propagating. And this turns the vector valued irradiance into really, or scalar valued irradiance into a vector valued irradiance known as the pointing vector. And I do not show the derivation, like I'm tempted to make a video out of this derivation because it might be very, very illustrating to you. But basically, it's the same math we already did. So the pointing vector S equals C squared times epsilon naught. And now instead of field amplitudes, I'm having the actual fields here. And now I'm taking the cross product of the two different field amplitudes, E and B. So here, and the amplitude S, the scalar S, the irradiance, is essentially now the modulus of this pointing vector S. And the amplitude S is the irradiance associated with the wave. And the pointing vector tells us in which direction this goes, this amount of irradiance, and also has the amplitude of irradiance information intact in place. So here, basically, I'm now replacing K with S, and this is fine when I'm propagating in vacuum. But if I would be propagating inside a medium, it might be the case that the K and S propagate in different direction. But I do not think we will go into this kind of questions at all during this course. We will leave that to the later courses, more advanced courses, when we are really treating birefringence of materials. And then we could, for example, understand that the S and K may not be always pointing in the same direction. Next, in what follows, I will calculate these pointing vectors in different scenarios so that I can show you how things can be calculated. And I will show you ways that how we can simplify these calculations so that the most of the time we do not even need to calculate these pointing vectors and the irradiances the hard way, but we can rather just use the easy way around. So the pointing vector S and the irradiance I, and I, of course, like it's the amplitude, the length of the pointing vector for a time harmonic plane wave can be calculated quite easily. And then this propagates along the direction of K as long as we're in vacuum. Sorry, the time harmonic plane wave propagates in direction of K, and we're interested in calculating the pointing vector for this entity. And the time harmonic plane wave oscillates at frequency omega, so that we can write the different field components. The E field is the field amplitude, the polarization of light E naught times cosine of dot product of K, wave vector, times the position vector R minus omega t. Omega is the angular frequency, and exactly the same kind of equation for the B field. And using the E and B fields, this kind of form, we can really calculate the pointing vector S as we defined it earlier. So S was written to be that it's the C squared times epsilon naught times cosine squared of K dot R minus omega t. And then this is the time and spatial dependence of the pointing vector. And then I'm calculating the vector products of the field amplitudes. So basically I'm just placing these into the equation of before for the pointing vector, and now I have a cosine squared, and then what's left is that I take the vector product of E naught and B naught. So that these are scalars, so of course I do not need to deal with these when I'm calculating the vector product of E and B. And we can see from here that this already tells us that the direction of propagation for S will be perpendicular to E and B. And also we know that the kind of strength of S is related to the E and B fields amplitudes. But we also know, looking at this, that we have this awful looking cosine squared term, that the vector S also oscillates quite quickly. So it also oscillates at the optical frequencies, and the angular frequencies at the optical regime is of the order of 10 to the power of 15 hertz, and this is quite fast. So if we would use any normal kind of electronic components that we could try to use and measure these kind of oscillation cycles, we would not be able to measure it. In fact, the kind of fastest oscillations we can measure with electronics are of the order of 10 to the power of 10 hertz. So then we can see that these kind of oscillation speed, the oscillation frequencies of Poynting vector and oscillation cycles of light in general, they are too fast to be measured using electronics. So in fact, we are not measuring this oscillation at all when we are measuring, but rather we are measuring some kind of time averages. And the kind of electrical components, instruments that we usually use to detect light are so-called photodetectors. And what they measure is that they measure the time averages of irradiances. So essentially quantities looking like this, and there the capital T denotes the time of averaging, how long we are measuring with the detector. And this is what we actually measure with these electronic components. And of course, the how much of light hits the light active surface of the detector also plays a role when we are measuring something. So let's now look into what kind of time averages we are associated with simple looking waves. So if we look at the time average of a simple sine or cosine oscillation, we know that actually that vanishes. So the cosine omega t, if we take a time average and with the t being just long enough, we know that this vanishes. And this is basically like a known truth from basic mathematics associated with sines and cosines. But the second power of cosine does not vanish anymore. And this is quite nice. So in terms of irradiances, so in terms of the Poynting vector, like we have the cosine squared relation, temporal dependence, and now we can rewrite this cosine squared into a form that we have 1 over 2, and we have 1 over 2 times the cosine of 2 omega t term here. And this again like goes to 0 when we calculate the time average, but definitely this 1 over 2 term does not. So that this 1 over 2 term is what persists when we are calculating or measuring the time average of Poynting vector. And now we know that we can calculate the time average of the Poynting vector, and this is a quantity that our photodetector would be measuring, or at least it would be measuring something that is proportional to this. We know that if we take the time average of a Poynting vector, then we are getting something like 1 over 2 times c squared times epsilon naught times the E and B fields, magnitudes, and their cross product. And we can calculate this now, and we have then calculated the time averaged amplitude of the Poynting vector S. And this of course means that we have means now to calculate the time average irradiance, so essentially the length of the Poynting vector. So the time averaged irradiance now is simply this, and then we have replaced the E field, E naught field, and the B naught field with their amplitudes, and then they're scalars, so we don't even need to calculate the cross product. And we can simplify this further so that we can calculate that the time average of the irradiance is 1 over 2 times c times epsilon naught times the E field amplitude squared. So often what we do is that we describe the strength of the EM field only by using the amplitude E0 of the electric field. And most of the time, especially in this course, we forget the existence of the B field. And looking at the above, it kind of makes sense that if you're interested in measuring of how much of energy is being transferred due to light propagating from point A to point B, we do not necessarily need to know anything about the B component. We can just calculate everything with the E field. So that this is kind of like rough motivation for this, that most of the time we do not need to worry about the B field. Another thing that we can use to kind of neglect the effect of the B field is that most of the optical materials, the vacuum permittivity, well, that of course is speed of light, but the material permeability, mu of materials at optical wavelengths, that's usually very close to the vacuum permeability, so that the B field really does not do much interesting in terms of optical wavelengths and optics. So this is a second kind of reasoning why most of the time we're only interested in the E field and not in the B field. So, like I already said, most of the time at optical wavelengths, we are fine in just looking at the E fields, and kind of proper motivation is that this is a good approximation, and especially for most of the materials when we are at or close to the optical frequencies. But if we would be having strongly magnetic materials, for example, ferromagnetic materials, then we should be more careful. But luckily for us, when we have ferromagnetic materials, most of the time light doesn't really propagate much through them, so that they're not that interesting materials from optics point of view. So that that's the kind of one of the motivations why we can most of the time just skip the B field and its existence. But be warned, it's an electromagnetic field, so of course there will always be the B field component associated with the E field. So nevertheless, it's always present there, even though we do not mention it or do much with the B field component. But it's always there. And now what follows, I will show way of how we can even simplify the calculation of the irradiance, so that in the future when we need to calculate the irradiance, you do not need to calculate the time averages at all. So let's assume that our field of interest, the E field, is of a form that it is again a time harmonic plane wave, so that the E field is field amplitude E0 times cosine of k dot r minus omega t, so simple time harmonic plane wave. Its irradiance can now be easily calculated directly by just using the field's amplitude. So the irradiance, which is the modulus of the pointing vector, we can calculate that it's the time average of c times epsilon naught times the field modulus squared, and we should calculate this time average. But we now already know that we can simply calculate that's 1/2 times c times epsilon naught times the modulus of modulus squared of the epsilon naught. So essentially, we do not really need to calculate the time averages much, as long as we're dealing with these time harmonic plane waves. And recalling superposition principle, even if you would have more complicated looking field, you could do this kind of calculation for each wave component, and then you could sum things up to actually know the irradiance of your more complicated looking electromagnetic field. And finally, let's look into the complex notation for the field and just verify that we can do the calculations also using them, and we end up with this familiar equation for irradiance I shown in this figure, in this slide here, so that we get back into this even using the complex notation for the electric field. So now we have time harmonic plane wave and its complex conjugate, and the complex notation gives us these two equations for the time harmonic plane wave. So the E will be of the form that we have the polarization of light, and we have the exponent IKR minus omega t form. So this is the complex notation for a time harmonic plane wave, and then the complex conjugate of the field. So that will be the complex conjugate of E naught times exponent minus I, and then the phase function KR minus omega t. And now using these, we can quite easily calculate the square modulus of the amplitude, because we can take use of the properties of complex number and its complex conjugate. So that the modulus of a field squared is simply the field and the dot product of the complex conjugate of the field. And now, since the phase functions, they have unity lengths, we only need to calculate the epsilon naught and the dot product of the epsilon naught with the complex conjugate of the epsilon naught. And this gives us the familiar form for the irradiance, so that we can reconcile the fact that it doesn't really matter. Do we use a cosine formulation for the wave or complex representation of the wave? The end results of calculations will be the same. So that the irradiance is 1/2 times speed of light c times epsilon naught vacuum permittivity times the modulus square of the field amplitude. And this can also be just written that it's the amplitude E naught times its complex conjugate E naught star. So this is what I wanted to say regarding irradiances and the Poynting vector. And maybe I have time to make some extra video regarding the Poynting vector. But if it confuses you and it feels that it will be something that you cannot really understand anything much about, hopefully it helps you when I say that the Poynting vector is a concept that is not the easiest to grasp, and we will not be focusing on that on our basic course, but rather you need to go into the more advanced courses where you start ending up in using Poynting vector. And even there, most of the time, the Poynting vector is rather only of a kind of pedantic interest, and it's not the kind of most important quantity to be working with in terms of the math. But usually we only deal with the E field, and that's it. So I thank you time now for following me all the way through this lecture. And next lecture, I will be speaking a little bit about the radiation pressure and the momentum associated with the electromagnetic field. So how, in addition of light being able to transfer energy from point A to point B, how it can also push things around while it's propagating. So I thank you for your time and patience, and I wish you a good day. Thanks and bye-bye.